So let's start talking about the entropy. We'll start talking about the spontaneous changes. These are changes that continue to happen naturally. Once started, a spontaneous change will carry on. A spontaneous reaction can be rapid or slow. Some people think that the spontaneous reaction means that it must be fast, but it can be of any speed. So to consider the idea of spontaneity, consider the following physical and chemical processes. This is a ball going down, it will not go up. This is a process of spontaneous reaction of the chain made from iron getting rusted. It cannot unrust. The iron combustion. After the iron, there is the combustion process. I can see the combustions happening spontaneously, but the reversible process will not happen spontaneously. And the dispersion of a gas inside our vessel also will happen spontaneously. I cannot get the particles of the gas coming up under this temperature and going together again to make the liquid under this temperature. What is the common characteristic that's happening to all the spontaneous process is an increase in a property called entropy. What is the entropy? This is a measure of the randomness or disorder of a system. The higher the randomness or the disorder, the greater the entropy of the system. What is the system? This is a part that's under investigation that we are talking about. So what is a spontaneous process? Is in an exam, spontaneous process is a process that occurs without external or outside interference. What are the driving forces for spontaneous processes? The driving forces are minimizing energy and maximizing randomness. Now let's try to define entropy. It's a thermodynamic function that measures randomness or disorder. State the second law of thermodynamics. The second law of thermodynamics states that in any spontaneous process, there is always an increase in the entropy of the universe. So the entropy of the universe is heading towards increasing. It will always start increasing and keep increasing. What is the third law of thermodynamics? Entropy of a perfect crystal at 0 Kelvin is 0, and we will see this later to explain. Now let's have a system which is magnesium and sulfuric acid reaction to form magnesium sulfate and hydrogen. Let's remember together what we meant by the system. The system is the reaction here that's happening, and what are the surroundings? The solvent is considered as surroundings. The air around it is surroundings. The test tube surroundings. Anything in the test tube like the thermometer is considered surroundings. So only the system is the magnesium and the sulfuric acid and the magnesium sulfate and hydrogen that's formed from it. So we have a natural progression from order into disorder. We said that the universe entropy increases, so the systems are always in the universe is moving from the order into disorder. We have moving from the lower entropy into the higher entropy. The gases generally have higher much entropy values than the liquids, and liquids have higher entropy values than the solids. Let's try to see which one has more randomness. A solid, which is perfect crystal here, the particles are all in a very perfect lattice, or the liquids, the randomness starts to increase, or a very high randomness inside the particles of the gas flying rapidly everywhere in a random and rapid motion. So as you go from the solid to the liquid and liquid to the gas, the randomness increase and vice versa. If you go from the gas to the liquid and from the liquid to the solid, the randomness will decrease and the entropy will decrease. So simple substances also with fewer atoms have lower entropy values than more complex substances with a greater number of atoms. If I have this molecule, nitrogen molecule made of 2 atoms, the possibilities for the entropy of these 2 particles is much less than this molecule of C2H6. This one has 8 atoms inside it. So the possibilities for the randomness and entropy with the 6 atoms is much bigger than the randomness that can be caused by only 2 atoms. So the more complex the structure, the higher the entropy it is. For similar substance of substances, the harder substances have a lower entropy. So I have diamond, the the diamond cannot be easily broken. So there are smaller particles that are formed, can be formed from it, while the graphite can be easily broken. It's weaker than the diamond, much weaker, so we can make different smaller pieces from the graphite, which can increase randomness. That's why the randomness in the graphite is much higher than in the diamond. The same reason causes something like lead to have higher entropy level than the calcium. For a given substance, the entropy increases as the solid melts and then changes to vapor. So when the solid changes into liquid and then the liquid changes into gas, you are increasing the entropy again as we compare the particles and how random they are. So there is a gradual increase in entropy also as the temperature of the substance increases. So the temperature will increase, the randomness and entropy is going to increase as well. Increasing the temperature of a liquid or gas increases the entropy because it increases the disorder of the particles. When substance melts or vaporizes, there is large increase in entropy because there is a very large increase in the disorder of the particles. So we'll see later how when you increase the temperature, the entropy of the substance increases. So this is the explanation what happens when you change from the solid particles into liquid particles, and when you change from the liquid particles into the gaseous particles, and how particles becomes more random and increases the entropy. I have calcium carbonate into calcium oxide and carbon dioxide. There is increase in entropy of the system because the gas is being produced. So here I have a solid that's changed into solid and gas. So instead of particles which are perfectly arranged, I'm getting a gas formed, so the entropy is going to increase. Here N2O5, when it's broken down into NO2 and O2, the gas is forming two types of gases. So I have 2 moles only of gas changing into 5 moles of gas. That's why the randomness increases and the entropy also is going to increase. Here reaction N2 plus H2 gives NH3. I've changed 4 moles into 2 moles. So the number of moles has decreased. So the particles that cause randomness decreases. So the entropy decreases. The particles decrease and the entropy or randomness decrease. Calculating entropy changes can be done when I look at the energy transfer. Let's imagine a system which is exothermic and imagine a system which is endothermic. If I'm moving from my system into the surroundings and then energy is transferred, this is an exothermic change. But if I'm going from the surroundings to my system, then it is endothermic. Imagine that surroundings is very big. This is the universe around me. So any change that I heat or lost or gain to the surroundings, it will not be felt too much. Imagine that you are transferring a small amount of heat to the whole universe around you. So imagine that the change that happens in the universe around you in heat is not that much. So if I have an exothermic reaction, the energy is released to the surroundings because this increases the number of ways of arranging the energy. The energy goes into the rotation and translation movement from place to place of molecules. So there is likely to be increase in the entropy. There will be increase in the entropy and increased probability of chemical changes. While if it is an endothermic reaction and energy is coming to here, there will be a decrease in entropy. Why is that? Because in the surroundings it has lost heat, so the movement of the particles will decrease and its entropy will decrease. We'll know the entropy as a symbol S. So the symbol S here will decrease, while here has it increased because I have moved heat to it. And since you have moved the heat to it and increased the temperature, we agreed that the entropy is going to increase with the increase of the temperature. So what is the total energy change? The entropy total is equal to the entropy in my system, that's delta S of the system, and the delta S of the surroundings. The change in the entropy of the system and the change in the entropy of the surroundings will give me the total entropy change. If the total entropy change increases, the entropy change is called a positive. So delta S is positive. For example, plus 40, joule, Kelvin, mole minus 1, and this is the unit for entropy. Reaction will then occur spontaneously. We say that the reaction is feasible and it can happen. If the total entropy change decreases, so it will be a negative delta S, and then we'll see that the reaction is not likely to occur. It's not a spontaneous reaction. It's a negative value for the entropy. So we agreed that delta S of the system is equal to delta S of the products minus delta S of the reactants, the same way we used to say that delta H is equal to delta H of the products minus delta H of the reactants. So let's see this question. Consider the following process. Calculate the delta S of the reaction zinc plus oxygen give us zinc oxide. I will just get the values. So the value of ZNO is 44 minus the value for Zn, which is 42, and half the value of oxygen, because this is O2, 205, while here I have one atom of oxygen. So I'll divide this by 2. So 42 plus 205, this all are the products, and this is the reactants. Subtract them from each other. You will find the result, which is 100.5 joule per mole per Kelvin. This is my unit. I can say joule per mole or Kelvin, or joule mole minus 1, Kelvin minus 1. Now take care that the units of the entropy is usually in joule, while the units for the delta H will be usually in kilojoule. So you have to take care of that while making the calculations. So the entropy change related to the delta H of the reaction can be calculated with this equation. The delta S, or the entropy of the surroundings, is equal to minus the delta H of the reaction divided by the T. So the delta H is the standard enthalpy change of the reaction. Delta T is the temperature in Kelvin, and standard temperature, this value is 298 Kelvin, which is equivalent to the temperature at the standard state. And when performing calculations to find S, we have, as we said, to note that delta H must be multiplied by 1000, because delta H is calculated in kilojoule, while the delta S is calculated in joule. So you have to change from the kilojoule into joule by multiplying by 1000. If you are changing from delta S into delta H, you will do the opposite. You will change from joule into kilojoule by dividing by 1000. So calculating the entropy as we agreed, the delta S surrounding is equal to minus delta H over T. And delta S of the total equal to delta S of the system plus delta S of the surroundings, all delta S of the system minus delta H over T. So if I remove the delta S of the surroundings from the previous equation, I'll put minus delta H of the reaction over T, so I can find that delta S total equal to the delta S of the system minus delta H of the reaction over T. I can use these two equations in my calculation. And then we'll see in the next session the Gibbs free energy.